All right, the topic of this video is going to be the introduction to what we call chemical equilibrium. And we're going to use the example of the cis to trans 2-butene conversion. Okay, so let me write up some of the things we learned from last time about that. One was that the energy profile looks something like this, where trans is slightly lower in energy than cis, and then of course you have an activation barrier to overcome, but the activation barrier is on each side. Okay, and so the other thing to write is the chemical reaction. We're going to call it cis goes to trans. Okay, so now when cis goes to trans, the forward rate is equal to the forward rate constant times the concentration of the cis molecules in molarity. Okay, so let's imagine we have only cis to begin with, and we have sufficient energy in our system to overcome the activation energy a large number of times. And so molecules start getting converted from cis to trans. Now, once we have some trans molecules, turns out they have enough energy to go back. And so the rate for the reverse is going to be the rate constant for the reverse times the amount of trans we have. And at some point, if we let this system run the reaction long enough, the rate at which it's going this way equals the rate at which it's going that way. And an equilibrium is established. And we call this chemical equilibrium, is when the rates of the reaction forward and reverse are equal. Okay? So now we're going to just do a little math. We're going to set them equal to each other. The rate forward equals rate reverse. Okay, and remember, we're going to define rate of reaction by definition to be positive, so we won't have any sign problems here. So that's K forward times the amount of cis equals K reverse times the amount of trans. And now we're going to solve for the amount, we're going to solve for the rate constants on one side. And the convention is to solve so that the product, whatever you're writing the chemical reaction as, the product is in the numerator and the reactant concentrations are in the denominator. All right, and so we have the concentration of trans divided by the concentration of cis, and it's equal to a constant. And it turns out that this is called the equilibrium constant, capital K. And we're going to use the little subscript C for equilibrium constants where the units are concentration in terms of molarity. Okay, so this is actually the simplest example possible. It turns out that you're going to learn how to write equilibrium constants for much more complicated reactions. The thing to realize is that it doesn't even matter how many steps there are if every step is reversible, so that you can get from the reactants to products and then from products back to reactants. Then you can write the equilibrium constant without even knowing the mechanism. So, for example, cis to trans isomerization can occur via a catalyst. Maybe multiple steps. Okay, and remember, a catalyst is going to lower the activation barrier, but maybe it has several steps producing several intermediate compounds. Well, it doesn't matter. The equilibrium constant is only determined by the trans concentration and the cis concentration. Not only that, but the ratio of the two is equal to a constant. It does not tell you that tran has to be a certain number or cis has to be a certain number, but the ratio does need to be a certain number for that temperature. So if we were to change the temperature, of course, the ratio of the trans and cis will change, because at higher temperatures, for example, it's a lot easier to get over the activation barrier, and might have unequal rates until we get a new equilibrium and get a new equilibrium constant. So we're actually going to talk about how K, capital K, depends on temperature. So just as an example, let's say we do an experiment and we find out that the amount of trans is 0.096 molar, and this is 0.064 molar. The equilibrium constant is 1.5. Now this is actually a very unusual equilibrium constant. Most of the equilibrium constants are very, very large numbers or very, very small numbers. And the other thing about the equilibrium constant is that if the equilibrium constant is greater than 1, we say it's product favored. Now in this, it's rather obvious what product favored means. It means it has lower energy, we have more trans. In complicated reactions where the stoichiometry is not just like 1-to-1, it's much more complicated, but we still speak of it being product favored, even though maybe there's even more reactant than product in a very complicated equilibrium constant expression. All right, well, that's the video for equilibrium kinetics.